So good morning, everybody. It's a really great pleasure today to receive and introduce Professor Hee Lee.
Are you sure this is still morning?
Yes, still in the morning.
Okay.
In Spain, yes, still in the morning. Actually, for me, it's really a great honor also to introduce Professor Hee Lee. And actually, I met him 20 years ago, almost 20 years ago. I don't know if you remember. I was presenting my first poster on carbon nanotube in Japan. And I don't remember anything about the conference, but I remember the very friendly discussion we have together, and you were really enthusiastic and interested in my work. I was very surprised. So thank you for so much enthusiasm you conveyed to me at that time. So Professor Lee is a director of the Center for Integrated Nanostructure Physics and also the Institute for Basic Science at the University Sungkyunkwan SKKU.
Not bad.
SKKU in Seoul. So he's also professor in energy science. He has a very broad research interest from growth of nanomaterials, including carbon nanotubes, CVD, graphene, and two-dimensional material like boron nitride and transition metal decalcogenide. He's also very well interested and expert in optoelectronics, thermal, photothermoelectric properties, excitons, charge transports, devices, and also energy harvesting. So, very briefly, Professor Lee was initially as a theoretician, so his thesis was on classical and quantum computer simulation. And then I don't know if you're still doing some simulation from time to time, but I think mainly he's supervising a very large group in experimental research. And he received a large number of prizes, and I think a very generous funding from Korea, which allow a lot of activities in his center. So I will present probably an overview about the main research direction there. Thank you, Professor Lee, for coming, and the stage is yours.
Thank you, Stefan. It's really nice to be here. This is the first time for me to be in Barcelona, also in ICN2. So I noticed this morning I met many professors here, and you guys are working on many different things, which I hope to find some common interest with our center. In the future, we should develop this collaboration. We are working on basically 2D layered materials, and the research area is quite wide, and I'd like to introduce some of our researches, and not all. I think it's only partial. So as much as time is allowed it. So let me start with this Nature Physics article. They introduce about what's going on in Korea, as you see from this red box. Our total GMP more than 4% investment for R&D. This is more than twice that of many other OECD countries. So you know Korea is always a highly technology-oriented country, but our government puts a lot of efforts on also developing the basic science as well. As you see from this article, again, IBS was initiated by the government with a strong emphasis on developing the basic science. Actually, this is sort of a historical in terms of budget, because each center is given like a $10 million per year. And this is also a long-term program. So 10 years is guaranteed. You can go. And the idea is to give this money to the director, and the director can choose their research topics, whatever they want, which is a completely freedom for us. It's like a dream for us. So we are working on in my center, we are working on these 2D layered materials. And also another point that the nature of physics also noted is some Korean university system, like our university, SKKU, is a private university, financially sponsored by Samsung. And many of the private universities in Korea are supported by the industry. Like a Postec, they are supported by POSCO, which is a steel company. So they provide a lot of money actually for the university. So Samsung, his profs are putting the largest amount of money to our university. So that's why our university is growing very fast. Now it's the #1 private university in Korea. Okay, so IBS is very similar to like Max Planck Institute. So we have a headquarters, but basically spread all these centers to each university. And we are one of them, which is located at SKKU. We are basically working on this 2D materials and I mean, including this graphene, boron nitride, and transition metal like chalcogide, and many other 2D materials. We are basically working on anything we like to, but focusing on this scalar dynamics and thermoelectrics. At the moment, we have 7 tenure-track faculty and about 30 postdocs working all together. And we also have, I think it's more than 100 graduate students, PhD students. And we have our own new building, which is like a 9,000 meter square. And this includes a clean room, dry room, vibration-free STM and TM rooms. This is our center. We have 3 buildings, actually. And this is our building, and this is another IBS, which is working on this brain science. This is another building which is completely empty at the moment. We are waiting for another director to take over. So, I mean, among, I think, more than 30% of the directors are actually foreigners. So we also welcome foreign scientists in our country as well. So let me start. If you look at this 5 months lecture in late 50s, there is I mean, this is very famous in nanoscience, so plenty of room at the bottom. But this lecture is actually quite long. It's quite lengthy, and you can read, and somewhere you'll find this sentence. What could you do with layered structures of materials with just the right layers? So he already predicted, although he's a high-energy physicist, he already predicted what's going on in material science, and one of them he looked at is layer structure. If you can control the number of layers, that means you have something new. So he already predicted this could happen, and this is what we are working on at the moment in, how long, maybe 60 years later, right? This is quite amazing. So I don't have to emphasize the vast range of the materials in 2D. If you choose, I mean, this is a carbon, which is graphene, and you choose this boron and nitrogen. This is a boron nitride, which is an insulating material, and you can also choose any chalcogen atoms and combine them with this transition metals in different stoichiometry, and you can find many different type of materials, semiconducting, metallic, magnetic, superconducting, whatever you can mention, you can do it. I think this is a freedom from the material science point of view. We can do many, many things. Of course, then there's a difficulty what to choose, well, depending on your favorite, I think. So I think one thing I like to emphasize with a 2D layered material, there's a technical relevance, which is very important. If you work with nanoparticles and nanowires, one most difficult challenge for technology is to assemble them together in a right way, which is very difficult. This is not just a simple technical challenge, but also related to semiconductor industry, and it's very difficult. I've been working on carbon nanotubes, and I know the difficulty of this. But if you choose 2D material, like a graphene, let's say, I mean, graphene shows only metallic behavior, but if you can work on it, you can fabricate the devices, millions of devices, by simply using top-down, the current technology. This is a great advantage, I think. So any kind of 2D material can stack them together, make the appropriate devices, and eventually you can simply do this top-down approach to integrate the devices. So this is perhaps one reason that Samsung is focusing on these 2D materials. Now, when you talk about 2D materials, of course, there are many interesting things, okay? One very common feature is no dangling modes, because the material itself in monolayer is stable by this van der Waals interaction. So they are very stable and robust. And plus, if you stack them on other material, you don't have to worry about this lattice mismatch and other stuff. So of course, there are some interactions going on, so you have to consider. But when you fabricate, when you synthesize these semiconductor materials into monomers or superlattice, you do have to worry about this lattice mismatch very, very seriously. But in this case, I think the problem is much less in 2D materials. And one interesting physics phenomena is this StrongCoulomb interaction. When you have charges in the 2D material, this charge sees clearly the other charges without much screening, because it's all air. So this reduced charge screening plays a very important role, for instance, in the case of forming these excitons. When you shine the laser onto the sample and we form this electron and hole pair, which is an exciton, and this binding energy of electron hole pair, this exciton, is very large because of this reduced screening effect. So this binding energy is proportional to 1/epsilon square. So the typical exciton binding energy in 3D is like a few tens of milli-electron volt, which is similar to room temperature. You cannot maintain this stability of these excitons at room temperature. But if you see this, very strong Coulomb interaction, you see this exciton binding energy is several hundred milli-electron volt, which is much larger than room temperature thermal energy. So that means you can maintain these excitons clearly, even at room temperature. I think this gives a lot of room for us. I'll show some examples. So this is a typical energy band gap, and the neutral exciton, typically in molybdenum disulfide, I think several hundred milli-electron volt. And it depends on the material, sometimes it's even higher. So compared to this room temperature, this is huge. And even for multi-exciton, like trion, if the system is n-doped, you can have negatively charged trion. Or if it is positively doped, then you can have positively charged trion. And this trion binding energy is further deeper by like 30 milli-electron volt. And even bi-excitons, the exciton-exciton interaction, this one is further stabilized by, again, 60 milli-electron volt from this exciton, neutral exciton. So there is also a chance that you may be able to observe this multi-exciton even in 2D material. I think this is a great advantage. So by simply having this power-dependent experiment, usually you don't see this kind of peak shift if you just have a neutral exciton. But because of this multi-exciton formation, we do observe this peak shift to the lower energy side, which is an evidence of forming this multi-exciton. This is very obvious even at room temperature. So we do have this multi-exciton formation. I don't want to go details, but once you say you have this room temperature exciton and multi-excitons, and you have this because of this strong Coulomb interaction, then you can take advantage of these excitons for many applications. One we are focusing on is this exciton transistor. The other one is multiple exciton generation, which we call MEG. And so to take advantage of this exciton in optical communications, we simply hybridize nanowire, in this case a silver nanowire, on molybdenum disulfide monolayer. You can see this is partially overlapped, and what you see is you just shine the laser onto this nanowire portion, and you get this very highly amplified photoluminescence peak. only neutral exciton, not the multi-exciton. If you use the high power, laser power, of course, you do have a contribution from this multi-exciton, but in this case, only neutral exciton. You can see, shining the laser on just the MOS side without this nanowire, you see this peak shift, which is a signal of this, sign of this multi-exciton formation. But in this case, when you shine the laser on just the nanowire portion, you can only see neutral exciton, and the multiplication is like 20 times, which is quite significant. So we actually tried to explain this one in terms of this cyclic behavior. What happens when you shine the laser, we generate plasmons in the nanowire. We generate also excitons in 2D material. And these two combine to form this surface plasmon polariton. And this guy transmits through this nanowire and get reflected at the end of the nanowire. And some of them is scattered, and we see this photoluminescence again. Some of them is reflected. So this, and then this one re-excite these excitons and plasmons again, and then coupled again, and again have this cyclic motion. So by keep repeating this cyclic motion, we can amplify this photoluminescence at this position. So we actually model this using theory, and it perfectly works. So I don't want to go detail, but basically you can take advantage of this idea to fabricate this, the optical components. In electrical circuit with a laser, what you have to do is you need to have this wavelength division multiplexing called. This is simply you shine the laser and then you choose a wavelength you want, okay, by the device. And you can also modulate this luminescence by electrical modulation, electrical gating, and eventually you have to detect this light at some point. So these are three major key components for optical communication devices. And actually we demonstrated all this in our paper, and it's very neat. You can take a look at it, this paper. And another phenomena that I like to introduce is this multiple exciton generation. Solar cell harvesting, I think everyone knows this solar cell. And but solar cell, we have a very wide spectrum. If you choose some band gap, like a silicon 1.15, we lose energy, lower energy side. Whereas we harvest this high energy side. But at the same time, some of the high energy light component, they lose energy by heating. So we lose actually energy quite a lot. Because of this limitation, we do have this fundamental Shockley Kaiser limit, where this solar cell efficiency reaches about 33%. This is a well-known fundamental limit. The question is how to overcome this fundamental limit. There is a way of taking advantage of this using this carrier multiplication. The idea is you shine the laser with a much higher energy than this band gap. We have some extra kinetic energy of electron, and these electrons actually excite another carriers by impact ionization. And then we generate two excitons instead of one exciton. So instead of losing this electron energy by heating the lattice, we can generate another carrier and multiply. So the photocurrent increases. So this is an idea, and people have worked on this one. In this case, the theory predicts one can reach up to 45%. Compared to 33%, this is quite a significant improvement. The question is, nobody realized this one yet with quantum dots or the other quantum nanowire system. And my question is, because of this strong electron-electron interaction in 2D, one can probably achieve this high energy conversion. Because electron-electron simply increases carrier multiplication phenomena. So we choose molybdenum ditelluride because this index band gap is like 0.85 electron volt, which is known to be the ideal number for this multiple exciton generation phenomena from theory. So we simply choose this material, but the material is not available in large area. So we had a problem because we need a large area sample, I mean at least a millimeter scale. So we have to work on this material. So in this case, we simply choose this material, this approach. Simply we prepare molybdenum thin film on the substrate and then provide a tellurium gas and telluride the whole system. This is not a new technique. Previously, people have tried, and then they failed because the volume expansion actually is a problem that breaks the sample once it forms this molybdenum ditelluride. But we had a careful experiment to not to allow this abrupt lattice expansion, but slowly expansion. So we were able to convert all this metal film to molybdenum ditelluride by simply annealing the sample very slowly. So originally this 1T prime phase, which is a metallic, they are converted into this 2H phase, which is a semiconducting. We like to have a semiconducting ones. This is actually stable. And as you see, this phase of 2H is gradually developing, eventually covers this whole area by 2H semiconducting phase. So we use this sample and measure this carrier multiplication phenomena. As you see, this is very ideal. If you have 100% conversion, you will have this stepwise structure. But no one demonstrated this stepwise behavior in quantum dots or nanowires. But in our case, we do certainly have this stepwise behavior. And if you try to fit this equation using this conversion equation, and we have this conversion efficiency almost like 99%, 100%, which is very surprising. And I mean, there are many arguments why you can have this one. We have an argument in the paper. I don't want to go detail. This is complicated. But I mean, the key idea is that this is a strong Coulomb interaction, okay? And another thing that I like to emphasize is a dielectric engineering. Now, the material itself is very much sensitive to the environment. So if you choose the environment as a different dielectric constant, you can actually modulate the band gap of the material by the screening effect again. So you just overlap two substrates with a different dielectric constant, and without touching the active material. Because of this screening effect, you do have different band gap screening, okay? Of course, if you measure photoluminescence, you do observe this extern. Of course, the extern binding edge is screened again. So these are two cancellation effects. So if you just look at the photoluminescence, you may not be able to observe this kind of difference scaling. But if you measure either photocurrent or scanning tunneling spectroscopy, you can directly measure the band gap shrinkage. And this is a theory that when people predict, if you choose this dielectric constant material from 1 to 20, which is very easy, you just simply choose a material like many other material. Then what happens is that the binary screening, I mean the changes from 25 to 500 millielectron volt. So this is not a negligible number at all. That means this is very important because without altering the active material, you don't create any dangling modes in the material, but instead just simply play with the substrate. And you can actually do band gap engineering. You can create quantum as super lattice, whatever, okay, by simply overlapping different type of alternative the dielectric constant material. It's very simple. I think this is one of our research targets. Recently, we are conducting. We are obtaining some results, but I didn't bring them here. And this is one example. How this band gap is shrink. We can simply choose a silicon substrate. In this case, just a pure silicon. So the very thin oxide layer, like a nanometer, is deposited on that. And we can simply transfer this MOS to on that and then measure this scanning tunneling microscope, STM. And by fixing the tip on the sample, we can measure spectroscopy. You can see, this band gap, conduction band and valence band, you can see they are changing due to this local strain. Okay, if you have a large strain, of course the band gap shrinks, okay? But if you have no strain, then you have this large band gap. So basically, what we believe in MOS2, we believe this band gap is like 2.6 electron volt. Real conduction band, valence band gap, okay? Now, if you use a different substrate, HOPG, which is completely flat, you don't expect this kind of modulation due to the strain. But the band gap in this case, 2.1. So the band gap itself is scaled from 2.6 to 2.1, which is great. You can actually play many things. Another interesting phenomena is this band structure. So for bulk MOS2, we do have this indirect band gap. But when you have a monolayer, we do have this direct band gap. So the transition from indirect to direct is a great advantage to have this very powerful optical properties. You know, I mean, there are some materials that does not show this. They actually opposite, like a gallium selenide. But in most of the TMD material, you find this kind of abrupt changes from monolayer to bulk. Now, there's also transport that can be modulated by the layer. This is an example of black phosphorus. You can simply change the thickness of the sample and you see the mobility changes. So, because of the surface scattering again. And not only the mobility itself, but also you see the karyotype is changing as well, from whole transport to like ambipolar behavior. So depending on the thickness. So you change the thickness and you change the work function of the material, and then this karyotype can be modulated. And so many of the properties actually strongly depend on this number of layers, so you can play with this. Another interesting phenomena that you can look at it in 2D material is 2D, what we call polymorphism. In 2D material, there are many phases that you can control, like hexagonal 2H, which is a semiconducting phase. And you can have this 1T phase, which is a metallic. And you can have this distorted octahedral phase, which we call 1T prime phase. This is also a very interesting phase. One can also play with this orthorhombic TD phase. One can have this rhombohedral 3R phase. They are all different. They show different behavior. And one thing more interesting is all these are interconnected with electronic structure. There are many quantum phenomena that reveals depending on this type of structure. So they are correlated. And the correlation between them is also a very interesting phenomena. We are working on it. And I'll show you some example. This is again the molybdenum ditelluride. The reason we choose this molybdenum ditelluride, because we can make sample, of course. And another one is, if you look at this molybdenum disulfide, which is very conventional one, you see that the energy difference between 2H and 1T or 1T prime phase, they are very much large. So you cannot control it easily unless you have this strong chemical doping like lithium intercalation. The material itself cannot have this stable transformation because of this large energy difference. But if you choose like a tungsten ditelluride, this is only a metallic 1T prime phase stable. But if you choose this like molybdenum ditelluride, you see the energy difference between this 2H stable and this 1T prime very little. That means you can play with it. And in fact, there is a stable phase existing, also in the 1T prime phase. And if you look at the literature, all days, okay. So we can actually make the sample by simply sintering. We can start with this 2H can be easily obtained by simply controlling this annealing condition. Okay, if you increase the temperature very high during sintering and quench rapidly, then you get this 2H more stable phase. And then if you slowly quench, you can stabilize this high temperature 1T phase and still maintain a room temperature. You can obtain this 1T prime phase. And the difference between this 2H and 1T prime, you see this dimerization of these molybdenum atoms, which is very similar to one-dimensional pilot distortion. So basically, when you obtain this 1T prime phase, you did this one-dimensional layers, one-dimensional nature from this atomic structure. So we can control it. And for instance, if you start with a 2H, and this is in situ temperature-dependent XLD experiment, you can actually see the phases shift to this 1T prime phase, 2H phase to 1T prime phase, which is evidenced by this peak shift. So we do have this controlling of the phase. And one can also, because this the transition temperature requires like 650 more than 650 Celsius degree, we wanted to play with this, for instance, IR sensing. And in this case, we want to reduce this transition temperature that works at the room temperature. So we actually try to reduce this transition temperature by simply applying the small strain. You can apply this strain, you can actually see this transition temperature is reduced up to 300, the room temperature, so that you can shine the laser and you change the phase from from 2H to 1T prime phase, which is similar to like a vanadium oxide. So this is the idea. But anyway, so only by applying only 0.2% of the strain, you can lower this transition temperature to room temperature. Is quite amazing. So another issue in 2D material is actually very notorious, this ohmic contact for transistor. Now, if you consider this ohmic contact in silicon, of course, can be done by this ion implantation. You can simply inject metals into this channel material near the contact, so then you have this ohmic contact. Okay, but if you have a monolayer, what are you going to do? You can simply break the material, right? So this is not easily done. And so in 2D layer, this approach is not very likely. People try this method as well, so, but I don't think it works. So again, this is a contact of metal with 2D van der Waals layered material. So we have to consider many, many things. People, of course, have this top contact, also side contact that induce this covalent bonding. And the issue is still not very clear. It's very different from graphene. We are working on it. And but we have to resolve this issue, to use this 2D material by any means to switching transistors. Okay. So the question is, of course, we do have advantage of having these different phases, metallic phases, semiconducting phases. If there is a way to convert this semiconducting phase to metallic phase at the contact area only, that would be great, right? You can simply remove this contact resistance. So, of course, MOS2, we cannot do that because we need this lithium intercalation, which is heavily chemical stuff, and physicists actually don't like it, and even the company don't like this idea. There's no way to, to control it precisely. So we actually propose this phase transition by light irradiation, which I told you. I'll tell you later. There's also a way to modulate this contact barrier, Schottky barrier height, using the boron nitride. So it's also very interesting. So here, the idea is simply to shine the laser onto some desired area for contact. And you can simply convert this 2H semiconducting phase to 1T metallic phase. Of course, the number of layers will be reduced because of this peeling up process. We have done this also using this graphene. And the same idea is also applied to this one. And you see this, if you look at this Raman, originally this 2H phase is converted into this 1T prime phase. So there is an evidence that we can do that. And you can also apply that to contact. So by simply shining the laser onto this contact area, and then later you just deposit metal on this. And you can have, originally this Schottky barrier, like 200 millielectron volt was reduced to like 10 millielectron volt. I don't say this is purely ohmic, but apparently the mobility of the system is increased by a factor of 50, okay? So this is also a very important approach. And perhaps technically this is relevant because it's light, so that's probably the reason that this paper is accepted in Science. And as I mentioned, if you just use HBN to improve this contact, yes, it is possible. So usually you can fabricate the transistor just MOS2, for instance, on deposit by putting on silicon oxide substrate. But then silicon oxide is very notorious to induce this charge carrier scattering. And by simply putting monolayer HBN in between, you can improve a lot. Of course, this has been practiced in graphene. Graphene mobility is greatly improved by putting the graphene sample on boron nitride. But how that happens, we don't know, actually, the detailed mechanism. So we do have some noise analysis and analyze this whole data. So by putting this HBN on MOS2, you can see even the metal insulator transition is observed. Previously, by putting that on SiO2, you don't observe that. And one function is to prevent these charge carriers from MOS2 to silicon oxide. So intrinsically, like an end-doping effect by preventing the charges from MOS2 to silicon oxide. So there's a significant doping effect. You can actually see that. And there's another effect. It also changes Schottky area. So by doing this BN replacement, you can actually see the activation barrier height is reduced significantly to like this one. And as a result, this contact resistance is reduced a lot, actually, using this approach. Again, whether this one shows this ohmic behavior, I don't know. Still, we see some variance in Schottky barrier height, which is small enough, but not completely zero. People also talk about superconductivity in 2H semiconducting phase. By simply injecting, putting this lithium or alkali metal intercalation, you can actually achieve this high TC like 10K. And you can also study with the pressure, or you can induce a superconducting phase. You can also play with a number of layers. You can also control this superconductivity as well. So there are many variables. But in our case, using again this molybdenum telluride, originally TD phase, and you can actually see this again superconducting behavior. And we can also do STM at low temperature. You see this superconducting dip, which is an evidence of this existence of this superconducting behavior. And what we found is actually, if you measure this magnetic resistance, you see the magnetic resistance depends on this molybdenum deficiency. No, I'm sorry, tellurium deficiency. So for low tellurium deficiency, we always obtain very high magnetic resistance, which means very pure material. And this magnetic resistance decreases as you increase this tellurium deficiency, which is perfectly acceptable. But what's more interesting is superconductivity. With this TD phase, with almost zero defects, we don't observe this superconductivity. Whereas as you increase this tellurium deficiency, we do observe this superconductivity. But the temperature is not very high, but still we observe this phenomena, which is related to this trade-off between this magnetic resistance and superconductivity. Don't know. I mean, it's also very interesting. So basically, you can do things, okay, with 2D materials. Of course, people talk about this base semi-metal, and I think MOT2 has been predicted as one strong candidate to reveal this base semi-metal. But we are not seriously working on this issue. But people are serious. Okay, so there are many things you can do. And also, I mean, with pure material, but you can also look for many interesting new physics phenomena by stacking them together. I think this is more important, and you will see this talks in the graphene flagship, graphene conference a lot. People talk about this heterostructure. So I'll show you just a simple example. Here we just use a molybdenum disulfide, and we can vary him by using this HBN layer with finite thickness, not monolayer. And then we can simply use gate at the bottom of this HBN, so we don't have to worry about this scattering from SiO2. In this case, what I like to show is this slope, which is a sub-threshold swing, which is an important parameter to reduce the power consumption, also the speed of the device. And the fundamental limit, we call thermal limit, is 60 millivolt per deck. And this one, usually you cannot achieve this number unless you really fabricate device very well. But in our case, it's almost, it's 69, up to 4 digits of current, okay? Which no one observed this one in 2D material, even for silicon devices. And if you look at this very bottom, we have here like a 63 millivolt, which is very close to the fundamental limit. And one reason that we have this really very ideal number is because of this low trap density, which is inherent from this HBN. HBN is really flat substrate that provides no trap charges. There is, still some, okay? It's not 100%, which is caused by the during the transfer. But this 10 to the 9 value actually is 1,000 times smaller than that of silicon oxide substrate. So this significant reduction of this trap density definitely improves this substrate thing. Again, when you form this heterostructure, there is also another issue. The two layers start interacting, and this causes a lot of trouble. And I think it's not a trouble, it's actually new stuff. So, for instance, we simply form this interface, molybdenum diselenide with a molybdenum disulfide. And of course, during this transfer, a lot of bad things are squeezed between these two layers. Then the interface quality is not very good. But once you anneal the sample carefully, then you do start observing these new peaks. Here, like photoluminescence from MOS2 only and photoluminescence from MOSE2. If you combine them together, not only these two peaks related, but also many other peaks. Like here, I call it this indirect band gap related new peaks. Also this interface peaks. So what happens when you have this heterostructure, and then there will be a charge transfer from here to here, there will be a whole transfer, and then we do form this interface new peak. Not only that, because you have another layer coming near, the band structure is renormalized. So you do have this renormalized band, which is a peak of this one. Actually, you cannot observe all these peaks. That is theoretically predicted, but no one observed all these peaks at the same time. In order to do that, you have to be very, very careful with this interface formation. And many people insist, they can observe, but nobody really observes this whole thing unless you pay attention to this interface. So having a good interface is a key. And another thing that I like to mention is you can simply fabricate again this MOS2 between two graphene layers, and you shine the laser, and you extract carriers from MOS2, and then we can extract the carriers, which is called photocurrent. But depending on how many layers you have here, so that's phenomena. So here we have just an exfoliated sample. We have this monolayer, and we have 6 layers. You can actually see very high photoluminescence in the monolayer. This is, but also very small luminescence from 6 layer. This is opposite because if you consider 6 layer, of course, more absorbance, definitely you see more absorbance, right? So you would expect a higher photoluminescence from this, but apparently it is not. Now, because this is because of this direct band transition from indirect band transition. This is bulk. This is monolayer, so the photoluminescent quantum efficiency, of course, definitely improved. But if you consider the sort of this rate equation, and you try to predict what's going on for this layer dependence, you see monolayer, they are deviating from this curve. So the regular classical rate equation wouldn't work. And we interpret this in terms of this sort of quantum tunneling phenomena. So we have this MOS2 monolayer, and we have a graphene and graphene, and in the middle we do have this charge, van der Waals charge, and we do have strong like electrostatic potential. Because of this different environment of graphene, here the Fermi level on both sides is different. So we have a sort of asymmetric electrostatic Coulomb potential. And when you excite carriers in MOS2, this one can easily transmit, but cannot transmit to this way. This is how it contributes to the photocurrent. Of course, if you increase the energy much larger, then there is no difference between these two. Then you have the same, and the photocurrent is reduced. This is actually what we observed, okay, in the device. And another thing, again, the simple demonstration, MOS2, and we have the source and drain, but in below, we have this HBN, and we have graphene layer. So the idea is to use only source and drain without gating and modulate this current, like a two-terminal memory device. How can you do that? We can do that actually, because once you apply the bias between source and drain, you can actually, this is a floating gate. There's no potential applied, but due to this built-in potential, we do have like tunneling from this drain to floating graphene. We have the charges accumulated in the graphene. But the potential drop occurs only here. We actually analyze all this using this capacitance coupling. And here there's no potential drop. So basically, the electrons tunnel through this one is accumulated in the graphene. And then you can actually use a small voltage to control the source and drain current. This one acts as a charge, a blocker. So if you have an electron coming, in this case, when you have charge, then the current is very low, right? But the whole current flows more dominantly. So actually, this is possible. One can actually store the charges, and then we use a small voltage here to operate this device. And then if you want to destroy these charges, you can apply the bias in negative direction. Oh, okay. And you can actually remove these charges and then come back to this original, and then you have also reading. So you can actually control this two-terminal device, which is very different from the conventional ReRAM or PRAM. This is very convenient. And also, one can use, so I'll skip. We have time for questions, right? So I'll go through all this. Okay. I think I can go through. So again, coming back to this, there's MOS2 on silicon. We do observe this phenomena before, and because of this local strain, actually, you can see the band gap is modulated, puddled everywhere in the sample. And if you do that on HOPG, of course, we don't observe that. So the strain, the local strain, is also very important to play with this band gap engineering. And you can actually see this band gap modulation with this radius curvature, and convert this into this band gap versus strain. And at some point, although we didn't intentionally create the strain, the local curvature, SiO2 substrate itself has this local curvature, and we do have this direct band gap region and indirect band gap region depending on this strain. And definitely the photoluminescence out of this should be very different, right? So, but we don't have this high resolution of photoluminescence in spatial resolution, but instead we can create this suspended MOS2. You can actually see this strong photoluminescence in the suspended area, whereas the samples on SiO2 substrate is completely quenched. So even though it's a direct material, unless you pay attention to this flatness of the substrate, you cannot have a high photoluminescence because of this quenching effect by the strain. So this is again the lesson that one has to be careful with these optical properties. Not only these optical properties like work function of the material, they can be also modulated. For instance, if you measure this work function in ambient condition, work function of MOS is like 4.36. But if you maintain the vacuum, then this becomes like 4 electron volt. And you come back again with this oxygen gas insertion, you see this value again combust. So the change of this work function due to this environment is not just a small number, it's like a 0.5 electron volt, which is similar to the work function modulation by the gate in graphene case. So you can also play with it with a 2D, the 2D type of material, the same principle. I think I prepared some more for the synthesis of the material, but I think I will have to stop. But my message is, I mean, 2D material itself is also very interesting, but I think more challenges is in heterostructure. So if you play with a heterostructure, there are many interesting phenomena, but again, you have to be careful to obtain the precise heterostructure phenomena, because this interface quality is very important to control everything. Thank you very much for your attention.
Thank you very much. It was a beautiful talk. So we can go for questions. I have several, but I can start. Yeah, I have one, which is when you have this very low sub-threshold slope on your vertical devices, the on current is enough for practical application, or?
Usually, silicon device require this value to be like 10 micrometer per channel. 10 micrograms per micrometer channel width. And this one, we have we have 10 to the 6, not still slightly lower. But what I like to emphasize, silicon device has a very high on-and-off ratio, picoamps. The off current. The off current is like picoamps. But in our case, the off current is like, nanoamps, okay? In our case, it's below, like 10 to the 14. So to reduce this power consumption in large integration, you definitely have to control this off current more seriously than on current. In our case, I think there is a hope we can use it because of this low off current. It's much less. This is the condition when the device dies, right? No power consumption is definitely the better, right? But in our case, we meet this condition, almost no current. So I think there's still a chance for 2D materials to play with.
Okay. Another question? Okay, fine. Let's go.
Hi. You have shown beautiful experiments on heterostructures. Actually, can you grow them sequentially, or they are made by transfer?
Okay, this is actually a very good question and challenging, I would say. So far, people have tried to grow this heterostructure, but in plane heterostructure, yes, there are some demonstration. But this stacking vertically, there are only 1 or 2 examples in a very small, limited, very small area. And our target is to grow this heterostructure in large area, in wafer scale. And this is not possible yet. The reason is because once you have this one layer, start grow another layer. This is basically dangling free. So the chances for other material to be absorbed on the surface of this 2D material is very less. So you have to play with something else. So in our case, we are working on this promoter. introduce another material to enhance this anchoring of the material. But we are still working on it. I don't say we can, but we are only limited in a small size of the sample, but like to expand this whole wave scale. This is our great challenge in the future. Thank you.
You mentioned that the external binding energy is very large in 2D materials, so 100 milli eV to one electron volt. What about the lifetime of extons? And then you mentioned also the exton transistor. Could you elaborate a little bit on that also?
Yes. The lifetime for interface exton should be longer than the regular lifetime of each material. In terms of, I don't bring this data, but nanosecond to picosecond and interfacial exton lifetime is several hundred picosecond or close to nanosecond. No, I'm sorry, several hundred to even longer. So definitely there is a longer lifetime. And then what is the second question? Aha, extern transistor. Okay. I think this is a topic that I like to give in the graphene conference. Again, we demonstrate this extern transistor by fabricating 2D materials with this 1D nanowire. You can actually transport this optical signal from one material to another by simply exciting this SPP, surface plasma polariton. This one propagates to the next layer and generate exton again from this material. And further, we can simply duplicate this many so that we can have many different wavelengths at the end, which is a multiplexing effect. You can also control the gate bias on each material to control this extern emission. Because when you have a very high free carrier, this free carrier screens the charges that are photoexcited, so reduce this photoluminescence. That way you can actually control this light intensity on-and-off ratio up to 200 in our case, which is the largest number ever existing. And you can also detect this photoluminescence intensity at the end of the wire, again to detect this signal as a photodetector. So we actually demonstrate all these functions in the device. I'm not sure whether this is, I can show you more data, okay?
No, we can discuss that. I have some questions.
I just have a small question concerning the wavelengths multiplexer. Typically, in current wavelengths multiplexing, the separation between the wavelengths is a fraction of a nanometer at around 1.5 micron. What you've shown are spectra that are extremely broad by comparison. So are you using a concept of resonance somewhere to separate the wavelengths?
No. In our case, we simply play with the material. So for instance, depending on what material you choose, okay, in our case, we use like a molybdenum disulfide and like a tungsten disulfide, which has like a 0.2 or 3 electron volt difference. And then you can actually detect them. But if you choose a material with a very narrow, difference, you can still manipulate, in principle.
What order of magnitude needs to be the difference between the intensity?
Okay. I just have a last question about, can we use this 2D material for thermoelectrics? Thermoelectrics.
I knew you were going to ask this question. Yeah, sure. We are working on also thermoelectric. We have been working on this antimony telluride system, but that's a bulk material. And I like to work with this 2D layer structure again. I think one interesting question is what happens when you have an interface to the heterostructure? How is this thermal conductivity and interfacial thermal resistivity changes? This is quite premature in our laboratory still, because we need to measure thermal conductivity at the thin layer. And one way to measure this one is to use this optical system like Raman. The other one, but people argue about it a lot, the accuracy of the approach. We are talking about, again, the device approach. And also, we are talking about TDTR, which is time domain differential thermal conductivity measurement, which is supposed to be precise. But it's difficult to get this system, and we are building up this system. We are almost done. So my main concern is what happens at the interface. And when you combine them together, then how does that change? So this will be our future work. I mean, for individual layer, we can do it simply, but for heterostructure, we do have to worry about many things.
Okay, thanks. I think it's time to finish. So thanks a lot,
Thank you.
Professor Lee. Thank you.